Everybody should be able to see my shared screen now. So this is the course for Calculus BC. I hope some more people show up and take advantage of it in the future. This is what the course is going to look like. We only have 6 sessions. So I am not going to explicitly cover the materials from units 1 and 2. That's the limits and continuity, unit 1, and definition of the derivative in unit 2. And we're not really going to touch on much of unit 3, which is the differentiation rules. We're going to talk about implicit differentiation today. That's actually part of unit 3, but that's really the only topic from unit 3 that we're going to cover. We've got a total of 10 units to cover. So in 6 sessions, it's just not possible to cover all 10 units. I think we may have, and we'll see how it goes today, but Victor and Sophie, since y'all, I think both North Atlanta and Grady require their students to complete Calc AB before they complete Calc BC. And so y'all have been through the AB material over a school year prior to this one. However, Barkley, I believe you've just taken Calc BC and you're in it right now. Did you start, Barkley, did you start in January?
No, I started in the fall.
Barkley, I can't hear you.
I started in the fall for Calculus BC, so it's a year-long course.
I guess you're gonna have to use your chat. We still can't hear you.
Okay.
I can hear you. I think something's going on with his microphone.
Oh, I guess I may not be able to hear anybody. Hey, that's better. Okay, Barkley, say that one more time.
So I started in the fall. It's a year-long course. It's
okay.
Calculus BC.
Okay.
Wait, Mr. Nichols, have you not been able to hear anything?
No.
Okay. Okay.
Okay. Yeah, and y'all, there's just 4 of us, so you can just unmute your mic and leave it unmuted. There's, unless there's like a baby crying in the background or the lawnmower or something like that, you could just leave your mic unmuted. That's no problem. All right, so Barkley, you and I will need to have a conversation kind of outside of class time, just to kind of figure out what might be the best strategy for you, because the large majority of the students who've signed up for the class have completed Calc AB before taking BC, and so the focus of this course is going to be the material, the C material, the material that's exclusive to Calc BC and is not covered in AB. Now, I am covering material from units 3 through 8 because, or 3 through 6. That's AB material. So we'll review some of it, just not all the AB material. Here's our goals. We're going to review the most critical concepts in each of these units. We're going to identify some power strategies for solving multiple choice problems, because brute force is not always the best way with these questions. Sometimes a little finesse will both make the problem easier to solve and take less time. And we're going to look at, when we look at free response questions, we're going to focus on clear communication and correct notation so that you maximize the points that you earn. Because at the end of the day, you don't have to get 9 out of 9 points on a free response question to get a 5. You generally, if you're aiming for a 5, you need to be able to get maybe 7 out of 9 points. If you're aiming for a 4, maybe that's 6 out of 9. If you're aiming for a 3, maybe that's just 5 out of 9. And those are averages across all the problems. And those are actually probably slightly higher than what's really required. Because of the limited scope of the class and the time we have together, my goal, what I'm aiming for, is helping you increase your score potential by 1 level. So if you feel like you're in the 2 zone right now, this course should help you get you up into the 3 zone, and 3s to 4s and 4s to 5s. Getting you from a 2 to a 5 is going to require a lot of work on your part outside of this class, and probably in conjunction with your current teacher. Each of our sessions is going to look sort of like this. They will be fast-paced. We are going to be focused on the exam and not necessarily on every little detail of the content. And they're going to be student-driven. So the Kahoot and a couple other things I've got built in are the way I'm going to make them student-driven. I want you to do the problems, solve the multiple choice and the free response problems before you come to class, so that in class I can collect some data and we can discuss those problems based upon the data that I collect. Basically, we're going to spend about half our time on multiple choice and about half our time on free response each class period. Y'all are all very familiar with Zooming, but please log in early so we can avoid any problems. Just to see, I'll have the Zoom open by 4:50 at the latest every day. If it's just going to be this smaller class, I really don't care about you muting yourself, but if the class gets larger, that's going to be necessary. Please do utilize the chat. I will always be able to stop and answer a question in the middle of, discussing a particular thing. So put a question in the chat and then just do the wave reaction and let me know, hey, go look at the chat, I have a question. And so yeah, so you can do the wave reaction to tell me you need a question, thumbs up, I'm good. And then the persistent ones, I'll ask you a question. And those are the ones where you have to open the participants list and choose one of those status. Okay, so all the session materials I'm going to post in Google Classroom because that's what the district has asked me to do. But if you have this PowerPoint presentation or this slides presentation, if you have it bookmarked, this is all you're going to need. Everything is linked from this slide deck, and I'm just going to add slides to it as we move forward. It's very much the expectation that you complete the pre-work before the session begins. And so, so I have it. So I'll email you in the next couple of days and post in Google Classroom about the pre-work for our next session. Okay, so here's what we're planning on doing for session 1. You got your pre-work there. Notice that these are links to the actual documents in Google Drive. The topics: implicit differentiation, L'Hopital's rule, interpreting derivatives in context, related rates, linearization. Y'all have done the Kahoot, and I'm going to look at those results here in a minute, and then we're going to spend the rest of the time talking about these 2 free response problems that you worked out. And I'm actually going to ask you to score your own paper and use this form link here for scoring the form to tell me what scores you got, so I can kind of have a summary of those. And again, I can get some data from you to figure out what we need to talk about. All right, so we are 23 minutes in, so let's get down to work. Let me take a look at this Kahoot and see what we need to talk about. So it definitely seems. All right, everybody got number 2 correct. Yay. So we don't really need to talk about that one. But we do need to talk about the other 4 problems. So we can go ahead and do that now. I'm going to switch over to my document camera so that we can look at these questions together. All right, so let's start right here with 61. We've got a differentiable function W, such that W of t represents the amount of water in a tank in gallons after t hours. What is the best interpretation of W prime of 4 equals 3? All right, so as we're reading the problem, we need to probably just circle, underline, highlight some important things. W of t is the amount of water in the tank in gallons after t hours. And then they want the interpretation of the expression W prime of 4 equals 3. Well, we know when we see W prime that we're talking about a rate of change in W of t. Now we just have to interpret what the 4 and the 3 means. Well, the 4 is our time. That's at t equals 4 hours. All right, we know it's hours here because it's after t hours. And then the 3 is the value of the rate of change. So the rate of change in W of t is 3. Now it's going to be the units of W divided by the units of time, because it's the units of it's the volume changing over time. So it's gallons per hour. So we're looking for the one of these that best expresses the fact that the rate of change in the volume of the water is 3 gallons per minute after 4 hours. All right, so let's see which ones of these we can mark off. Which of these 4 can we automatically mark off as just totally unacceptable?
D.
Say that again?
D.
D, the average amount of water, right? Okay, great. The derivative on its own says nothing about average value, so definitely not D.
And A.
The amount of water in the tank. Okay, so this statement A is just about the amount of water. There's no reference to rate of change here. Okay, so it can't be A. So it comes down to B and C. Well, let's see here. B is a statement that says the amount of water in the tank is increasing. Statement C says the rate of change in the amount of water in the tank is increasing. So which of those is true? Is it the amount of water that's increasing, or is it the rate of change in the amount of water that's increasing?
Is it B?
So the amount of water in the tank is increasing at a rate of 3 gallons per hour. So yeah, so because we're doing W prime of 4 equals 3, that is the derivative of W of T, which means it's the rate of change in the amount of water. So that means the amount of water is increasing. They didn't use the word rate of change, but they said increasing at a rate of. So we've got the quantity here that is changing, it's the amount of water, and then the rate at which it is changing. So choice B is correct. Notice that we also have at T equals 4 hours. So that looks like B is good. The problem with C here is that it uses the phrase rate of change in the amount of water. But then it says that rate of change is increasing. Well, if you're talking about a rate of change, the rate at which a rate of change is changing, this is a statement about W or double prime, W double prime of T. Okay, so that would be a statement about that, and that's not what we have here. We're talking about just the rate of change in the volume, not the rate of change of the rate of change in the volume. Okay. There's the acronym that I like to use, and there's a couple of different versions of this. Some people just say NUT, nut, noun, unit, and time, but I like to stick an R in there. So it's either NERT or turn or NRUT, I don't care which one, but there's got to be some reference to the rate here. So I've got those 4 things underlined here in my sample response. The noun here is what is changing. So in this case, it's the amount of water in the tank. That's our noun. The rate is the statement that this is increasing at a rate of 3, whatever. Okay, so always interpret the sign of the derivative. In this case, the derivative was +3, so that positive means it's increasing at a rate of 3. And then, okay, here's our units, gallons per hour. We knew that volume was measured in gallons and time was measured in hours. So the rate of change in the volume over time would be gallons per hour. And then finally, the time reference at T equals 4 hours. Now, in terms of English, there's lots of different ways that you can restructure that sentence, but it's got to have those 4 components in it to get full credit. They like asking these questions in the free response. And so you really do have to actually construct an English sentence that conveys all those things. Questions or comments about that one? Then let's move on to the second problem, which is 65. This is another question about interpreting the meaning of a derivative. So in this case, W of T represents, so W of T is the rate at which water enters the tank in gallons. The rate at which water enters the tank in gallons. So there's a typo there. That would have to be gallons per day. after t days. So notice here that the function w of t, there's no prime there, but they're telling you that w of t represents the rate at which the water enters the tank. So w of t is a derivative. You can think of it as being, it's v prime of t, if you think of v as volume. So w of t is the rate of change in the volume, okay, or volume that's going in, let's say volume in, okay? In the same way, r of t represents the rate at which water is removed from the tank. So r of t is another volume derivative, but it's the volume going out, so in and out. So if we want, which of the following expressions would represent the rate of change in the amount of water in the tank that is decreasing at t equals 1 day? Okay, well, this is a in and out problem. So the volume is increasing at a rate of w of t and decreasing at a rate of r of t. So the net change, or the net rate of change, is going to be w of t minus r of t. So the rate in minus the rate out gets you the net rate of change in that volume. Well, if we want it to be decreasing after t equals 1 days, we know it's going to be a statement about w of 1 and r of 1. And then decreasing means that rate has to be negative. So that's choice C. These rate of flow or rate of change in, rate of change out questions are quite common. And in these types of problems, they almost always just name the rate of change functions as w or r of t without explicitly calling them a derivative, because it's your responsibility as a student is to recognize that derivative in the context of the problem. Okay, anything else we need to talk about there? Well, then let's take a look at the next one. That is, now this one is the one, is this the one everybody got right? Did I say it was the third question? Oh no, it was that second question that everybody got right. I didn't need to talk about that as much. Should pay more attention. Okay. Well, then let's look at 67 here. It's about particle motion. And I picked this one because this is what is typically the most difficult type of particle motion problem that you're going to see from Unit 4, from the first half of the course. We got a particle that moves along the x-axis, which they're telling you here that it's linear motion. It's moving along a straight line, which makes the problem a lot easier. Y'all are Calc BC students, so later in Unit 9, you're going to be dealing with points moving in 2 dimensions. Okay, but this, because they're telling you it moves along the x-axis, we know, okay, it's 1-dimensional motion, it's linear motion. I don't need to use any BC stuff. I can just use Calc AP things. Okay. All right, we got time bigger than 0. It's moving along the x-axis, so we're only looking at positive time, and its velocity is given by the function v of t equals 2t squared minus 6t. Which of the following statements describes the motion of the particle at time t equals 1? Well, if we skim the multiple choices, you will notice that these statements are mostly about, is the particle speeding up or slowing down, or neither, or is at rest? When you have a question that involves speeding up or slowing down, you have to consider both velocity and acceleration. So it didn't just ask you, is the velocity positive, is the acceleration positive or negative? It didn't tell you what direction is it moving in. It's you need to know both velocity and acceleration to determine whether it's speeding up or slowing down. Well, we need to know the sign of the velocity at t equals 1. Well, that's at 2 minus 6, negative 4. All right, so that's definitely less than 0. So what does that tell us? What does the fact that the velocity at time t equals 1 is less than 0? What does that tell us?
Wait, does that mean it's going in the opposite direction?
Okay, it does tell us something about the direction of motion. So velocity is the rate of change in position. So it's x prime of t. So the rate of change in position is negative. So when a rate of change is negative, that means what's happening to the quantity, in this case, x of t, the actual position, if the rate of change in the position is negative. So just in general, a negative rate of change tells you what about the quantity?
Is it just that it's decreasing?
Yeah. So a negative rate of change tells you that the quantity is decreasing. So this velocity is the rate of change in position, the rate of change in the x coordinate in this case. And so because that rate of change is negative, that means the x coordinate is decreasing, which in this context means the particle is moving to the left. Right? Your position is decreasing on the x-axis, means you've got to be moving to the left. So that's what I'm going to note here, moving left. Now, none of these statements are about direction of motion, but we still needed to know that information because figuring out whether it's speeding up and slowing down, we need to know both velocity and acceleration and then draw a conclusion from the combination of those two things. Well, they didn't give us the acceleration function, but we know it's equal to the derivative of the velocity function. Acceleration is the rate of change in velocity. So we just need to take a derivative of 2t squared minus 6t, so that's 4t minus 6. Well, now we want to know the sign of the acceleration at t equals 1. Well, that's just going to be -2. Well, that is also 0 or less than 0. So it is moving left. That's what the velocity being negative told us. The acceleration being negative means that it is accelerating left. Or let's say it should be, talk about, yeah. So if it's moving left and accelerating to the left, so it's moving to the left and its speed is increasing as you move, well, excuse me, yeah. It's moving left and getting faster. Even though the acceleration is negative, because the velocity is also negative because it's also moving left, these two things being negative tells me that the particle is speeding up. So the only answer here that includes speeding up is choice A. So general rule of thumb here. For speeding up, you're looking for the velocity and acceleration have the same sign. You have to compute both of them. If they're both negative, it's speeding up. If they're both positive, it's speeding up. Think about it as like vectors and from physics. If your velocity vector and your acceleration vector are pointing in the same direction, that means the object must be getting faster, even regardless of what direction they're moving in. If the velocity and the acceleration vectors point in the same direction, the particle's the speed is increasing. Now, on the other hand, slowing down means that the velocity and the acceleration have opposite signs. Doesn't matter what those signs are as long as they are opposite. And that tells you that it is slowing down, because if you're moving to the right, but acceleration is negative, pointing in the negative direction, that's kind of like you're being drug, the speed's decreasing because you're moving to the right, but the particle's got to be slowing down in order, because that acceleration is pointing in the opposite direction. So how do we do on that one?
Good.
Okay. There are several other particle motion questions in the problem set that I gave you. But just for sake of time, we're not going to have time to talk about them, but I would encourage you to go and look back over those and make sure you can answer them. I'm going to give you the answers to all these multiple choice questions after our session ends. All right, see here, the fourth question was number 72, the block of ice in the shape of a cube. Okay, there's something I need to make a note of. A cube melts uniformly. Well, it's melting, that's important, maintaining its shape. So it's always a cube and it's melting, which means its volume and its dimensions are decreasing. The volume of a cube is given a side length is given by V equals S cubed. Okay, so volume equals the side length cubed. I don't think they're going to give you that formula in most cases. They gave it to you here, I think, is just a little helper, but the volume of a cube, you should know that's side length cubed. Okay, at the moment when S equals 2 inches, so the side length is 2 inches, the volume of the cube is decreasing at a rate of 5 cubic inches per minute. All right, I think I'm gonna have to start writing things down. We've got volume equals S cubed, and then we got the statement that when S is 2, the volume of the cube is decreasing. All right, so we're talking about the rate of change in the volume, dV over dt. But it's not just the generally dV, it's the dV over dt when S equals 2 inches. The big vertical bar there just means at or when or such that, however you want to read it. That's just standard math notation. And that quantity is 5 cubic inches per minute. So 5 inches cubed per minute. All right, so that's what we know so far. What is the rate of change in the side length of the cube? Okay, so ds over dt is the rate of change in the side length with respect to time. So ds over dt, that's with respect to time, in inches per minute at the moment when s equals 2 inches. So when s equals 2, we want to know the value of that rate of change. So again, s equals 2 time inches per minute. Okay. They give us information about one rate, then they ask us a question about another rate. So we're going to find the unknown rate by relating it to the given rate, which is why we call this type of problem a related rates problem. Okay, they give us information about one rate and then ask us to find the value of a second rate. We're going to do that by taking the volume formula that they gave us, because it involves these two variables, the V and the S, the dependent variable from the given rate and the dependent variable from the unknown rate. It relates those two variables. Well, we know that V equals S cubed, but we want a formula that relates dV over dt to ds over dt. So we're going to take our volume formula and we're going to take the derivative with respect to time of both sides of that equation. All right, well, that would mean, so on the left-hand side, the derivative of V with respect to t is dV over dt. The derivative of S cubed, now that's a power rule, 3S squared. But here, S is not the independent variable. S is a function of time. So you might think of this as S of t squared. So because this is a function of time, it's since S here is a function of time, V of t equals S of t cubed. Everything's in terms of time here, so I've got to use the chain rule because this S of t cubed is a composition. So that means I've got to multiply by the ds over dt. So we've got the derivative of the outer function there. That's the derivative of the cubic function, multiplied times the derivative of the inside function with respect to time. Well, we need to know the value of ds over dt given the value of dv over dt. Well, it looks like we can start plugging some things in here. I'm kind of run over, I'm gonna go down here because I'm running out of room. All right, so we know that dv over dt is equal to 5 inches cubed per minute. So here we've got 3 times s of t squared. Well, I need to know what is the value of s of t at the instant at which we're solving the problem? What goes there?
S of 2.
Yeah. Well, not s of 2, it's s equals 2. So it's just 2. Because they told us that we're solving this problem at the instant in time when s equals 2. So the value of s there is just 2. All right, and then we got to multiply times ds over dt, but that's what we're trying to find. We don't know ds over dt. And technically that's ds over dt when s equals 2. Well, but there's only one unknown in that equation now. We can solve for ds over dt. Let's see, this would be 4 times 3 is 12. So divide on 12 on both sides, you get 5/12 equals ds over dt when s is 2. Well, I believe we've got our answer. Choice B. Let me double check and make sure I didn't make an arithmetic error. See, that's 72. Oops, something should be negative. Let's see here. So I made a mistake. See if you can find my mistake. It's not a computational mistake. Computations are correct.
Let me my question, because it said it was decreasing at a rate of 5 cubic inches. So I was going to ask, why is it not negative to 5?
There you go. So this rate up here, the dv over dt, should have been -5 cubic inches per minute, which means that's -5, which means this is -5/12, and our answer is not B, it's A. All right, all right, let's take a look at 76 and then we'll be done talking about multiple choice, but we've only got 10 minutes left because these sessions are too short. Okay. All right, so 76 is a problem that involves L'Hopital's rule. They ask for the limit as x approaches 4 of f of x divided by x squared minus 16. They gave us the graph of f of x. And what we notice is that the limit as x approaches 4 of f of x, well, 4 is right here. No, excuse me, 4 is right there. And so that y value is 0. The limit of f of x as x approaches 4 is 0. The limit as x approaches 4 of x squared minus 16. Okay, x squared minus 16 is continuous. So that's just got to be 4 squared minus 16, which is also 0. So the limit of the numerator is 0. The limit of the denominator is 0, which tells me we're allowed to use L'Hopital's rule. So the limit as x approaches 4 of the quotient, f of x divided by x squared minus 16, is equal to the limit as x approaches 4 of f prime of x divided by 2x. I took the derivative of the numerator and the derivative of the denominator by applying L'Hopital's rule. Well, now let's go back to our picture. We now need to check what's the value of f prime of 4, because we're going to try direct substitution. Well, f prime of 4 is defined. It's the slope of the line passing through 4. Well, what is that slope? Well, it looks to me like it is fall, run, run 1. So it's a slope of -1. So the limit as x approaches 4 of f prime of x is -1. It's the slope of that line segment. Well, 2x is a nice continuous function, so that's just going to be 2 times 4, which is 8, which is our choice C, which matches up with what I've got down as the answer. This part that I wrote down here, where I checked the limit of the numerator and the limit of the denominator, in a multiple choice question, that's a mental check. There's really no reason to waste the time of writing that down. However, in a free response problem, you will not receive full credit on this problem unless you write both of these things on your paper. That you must; those are the conditions for the L'Hopital's rule. So you either got to have 0 over 0 or you got to have infinity over infinity. And by the way, writing anything like this or this or even that does not get you credit for verifying the limit of the numerator and the limit of the denominator. None of that stuff works. In fact, these two statements right here may just get the entire problem counted wrong, because those are mathematically that's incorrect notation all day long. It's meaningless. So do not write those things on your paper. This is good for just quick mental checks using that notation. But on a free response problem, you got to be more formal. You got to write it out using the full and correct notation. Okay. Questions, comments on that one? Okay, so I'm going to forego the data collection on this one just for time. I only got 8 minutes left, and I want to make sure we hit some of the high points here. We've got this problem here where we've got the temperature of a mug of coffee that's given by C of T. They tell us that C of T is decreasing and concave up. Well, that tells us that C prime is always negative and C double prime is always positive. So we need to make notes to ourselves about what they're telling us. All right, the units here are that C of T is in degrees Celsius, so that means C prime is going to be in degrees Celsius per minute, and C double prime is degrees Celsius per minute per minute. Okay, the rate at which the temperature changes given by C prime of T, measured in degrees Celsius per minute, and selected values are given in the table, is also known that C of 4 equals 40. So that's the only piece of information we know about the actual temperature, that the temperature of the coffee after 4 minutes is 40 degrees Celsius. So in part A, they say, using correct units, explain the meaning of C prime of 8 equals -3 in the context of the problem. Now, this is another of those noun, unit, rate, and time. Okay, so time, so after 8 minutes, the temperature of the coffee is decreasing at a rate of 3 degrees Celsius per minute. So we have the time, the noun, temperature of the coffee, the description of the rate decreasing at a rate of 3, and then the units, degrees Celsius per minute. In this case, the way the rubric is written, you have to get correct units throughout the entire problem to get the units correct. So here in part A, you just had to have the time, the noun, and the rate parts here to get full credit for part A, because the units are counted separately throughout the problem. For part B, using the data in the table, estimate C double prime of 3, and then using correct units, explain the meaning of C double prime of 3 in the context of the problem. Okay. This is one of those situations where they're really nitpicky about the supporting work that's required. If you're approximating the value of a derivative, you're always going to approximate that by using a difference quotient. So in this case, since we're calculating C double prime of 3, so that's the rate of change of the rate of change, that's a difference in the values of C prime divided by the corresponding difference in T. You have to write the difference quotient some form, either this difference quotient or the one with the numbers plugged in, to get credit for that estimate. If you just write C double prime of 3 is approximately 1, and that's the only thing you write on your paper, you won't get credit for the calculation. You have to see one of these two supporting pieces of work. In fact, if you write this and only this on your paper, you get full credit. You don't have to algebraically simplify expressions to get credit for them. Now, they did ask us for the interpretation. So again, it's after 3 minutes, time is 3. The rate of change in the temperature. So this expression is C double prime of T. So that's a rate of change of the rate of change. So the noun here is the rate of change in the temperature. And then that rate of change in the temperature in the coffee is increasing at a rate of 1 degree C per minute, all right? Because it's the rate of change. So 1 degree Celsius per minute. Okay, so for part C of the question, write the equation of the tangent line to the graph of C of t at t equals 4, and then use your tangent line to approximate C of 5. Is your approximation an over or under estimate of the true value of C of 5? Okay, so our linear approximation, which I'm calling the function L of t, well, is just the equation of the tangent line. Tangent line is always the y value at the point of tangency, which in this case is C of 4, plus the slope at the point of tangency, so C prime of 4, times, in this case, it's t minus the t value at the point of tangency. So our point was 4 comma C of 4. Well, they told us that C of 4 was 40. They gave us that information. So this is our point, and then our slope is C prime of 4. Well, C prime of 4 is given in the table. We've got values of C prime at t equals 4. The slope of the rate of change is -8. So we got a slope, we got a point, we can write the equation of the line. So it's the y value plus the slope of -8 times t minus the t value. So this is the equation of our tangent line, or quote unquote, the linearization. So now we're going to use the linearization to approximate C of 5. So C of 5 is approximated by L of 5. And L of 5 is just, well, we plug T equals 5 in. Well, 5 minus 4 is 1, 40 minus 8 is 32. So our approximation is 32 degrees Celsius. They did also ask us whether this was an over or under approximation. Recall that they told us at the beginning of the problem that C of t is concave up. It's concave up and decreasing, so it looks something like this. If I draw kind of just a really approximate picture. Any tangent line that I draw to a concave up curve lies below the curve. So that means any estimate that I get from the linear function is going to be an under approximation. So since C of t is concave up on this interval, and by the way, you've actually got to state the interval, not at a point, but on the interval. The linear approximation is less than C of 5. That is, C of 5 is bigger than the 32 degrees Celsius that was predicted. In part D, And this is going to run just a little bit over, but I think we'll be okay. A muffin is taken out of the oven at the same time as the coffee is cooling. Temperature of the muffin M is modeled by the relationship M equals 1/16 C squared, where C represents the temperature of the coffee after T minutes. Using this model, find the rate at which the muffin is cooling with respect to time at T equals 4 minutes. Okay, so the rate at which the muffin is cooling is M prime of T, and then they wanted it T equals 4. So what we're looking for is the value of M prime of 4. Well, they told us that M of T is equal to 1/16 C squared. Well, C is a function of time. So I want to record that here as C of T to remind us that when we take the derivative of M with respect to time, we're going to use the power rule. 2 times the 16th is an 8th, and then the power gets dropped down to 1. But because this inside function here is a function of time and we're taking the derivative with respect to time, we also got to multiply times the derivative of the inside function. So times C prime of T. Now we've got a formula we can plug into. We want to know M prime of 4. So that's going to be 1/8 times C of 4 times C prime of 4. They gave us that C of 4 is 40. We've read from the table that C prime of 4 is -8. So an eighth times -8 is -1. So we get -40 degrees C per minute. Technically, part D here is a related rates question, but it can be solved pretty straightforward just by thinking about the chain rule. We're not going to have time to do the other free response question that I assigned, but I will post the solution and the rubric to that on Google Classroom for reference. As you study this material over the next week, you've got other multiple choice questions in this problem set, and you've got additional free response questions that we have not solved. I haven't written out solutions to all the free response questions, but if you have one in particular that you want to ask me about, just send me an email and I'll write the solution down and send it back to you. As far as the multiple choice, I will post those answers as well. All right, folks, as you can see, this hour goes by real fast. So if next time, be here early so that we can start right at 5 o'clock. I will have the presentation link posted and the Kahoot link up, and so you can go ahead and do those things ideally before 5 o'clock, but at the very least like right at 5 as soon as class starts, so we don't have to wait around. All right, it's been good, folks, but I'm going to call it a night. Y'all have a good week, and I'll see y'all next Tuesday. Bye.
Thank you, Mr. Nichols.
Bye.